A decoder receives an n-bit binary code and activates exactly one of its 2 to the n output lines. Think of a mailroom sorter. The n-bit address is the zip code and the 2 to the n output bins are the possible delivery routes. Only the matching bin opens. Symbolically, it is drawn as a block with n inputs, often labeled a sub n-1 through a 0, and 2 to the n outputs, y0 through y2 to the n-1. An encoder does the reverse. It looks at 2 to the n input lines, finds the one that is high, and produces the corresponding n-bit binary number. It is like a sensor that tells you which hallway light is on. The encoder symbol has 2 to the n inputs, I0 through I2 to the n-1, and n outputs, b sub n-1 through b0. Many textbooks also show an enable, en, input that can turn the whole device on or off. Explanation: to write a truth table for an n to 2 to the power n decoder. List all 2 to the power n possible input combinations 0, 0 to 1, 1, 1, 1. For each row, only the output whose index matches the binary value of the inputs is set to 1. All others are 0. For example, a 2 to 4 decoder has inputs a sub 1, a sub 0, and outputs y sub 0 to y sub 3. When a sub 1, a sub 0 equals 1, 0, binary 2, the truth table shows y sub 2 equals 1, and y sub 0 equals y sub 1 equals y sub 3 equals 0. From the table you can derive a Boolean equation for each output. yi equals the product over k equals 0 to n minus 1 of a sub k raised to the b sub I comma k times a bar sub k raised to 1 minus b sub I comma k, where b sub I comma k is the kth bit of I. For an encoder, the truth table is the opposite. For each input pattern where exactly 1 I sub j equals 1, the output bits equal the binary representation of j. The Boolean function for each output bit is a sum of products of the input lines that correspond to a 1 in that bit position. For example, B0 equals I1 exclusive or I3 exclusive or I5 and so on. A 1 to 2 decoder needs 1 NOT gate and 2 AND gates. Y0 equals NOT A and Y1 equals A. A 2 to 4 decoder uses 2 NOT gates to generate not a sub 1 and not a sub 0 and 4 AND gates each with 2 inputs. Y0 equals not a sub 1 and not a sub 0. Y1 equals not a sub 1 and a sub 0. Y2 equals a sub 1 and not a sub 0. Y3 equals a sub 1 and a sub 0. No OR gates are needed because each output is already a unique minterm. For a 3 to 8 decoder, you add a third input a sub 2 and generate its complement. Then 8 3-input AND gates produce each yi equals the product of either a sub 2 or not a sub 2, and either a sub 1 or not a sub 1, and either a sub 0 or not a sub 0, matching the binary index. The pattern is clear. Each output is the logical AND of either the true or complemented form of every input, forming a minterm of the truth table. A binary encoder takes 2 to the n inputs and produces n outputs. The simplest 4 to 2 encoder uses the equations. B1 equals I2 plus I3. B0 equals I1 plus I3. If more than one input can be high, a priority encoder resolves conflicts by assigning a rank to each input line. The highest ranked active line wins. For a 4 to 2 priority encoder with I3 highest priority, the Boolean equations become B1 equals I3 plus I2. B0 equals I3 plus I1. V equals I0 plus I1 plus I2 plus I3. Adding an enable n input means each output ANDs with n. Yi equals n and logic function. This prevents the encoder from reacting when the system is disabled, similar to a gate guard that only lets traffic in when a signal light is green. Both decoders and encoders can be built from only NAND or only NOR gates, which is useful when a technology library provides just one universal gate. To make a decoder with NANDs, note that a NAND behaves like an AND followed by NOT. Since each decoder output is already a complemented and a minterm, we can obtain y sub I by NANDing the appropriate literals, and then adding a final not another NAND fed with its own output, if a true non-inverted output is required. For example, y3 equals not a 1 a 0 is directly a NAND of a 1 and a 0. For a NOR-only encoder, first implement the OR sums using De Morgan B. 1 equals not of not I2 and not I3. Thus, a pair of NOR gates can generate the required OR, and a final NOR can provide the inversion needed for the priority logic. This conversion reinforces the principle that NAND and NOR are functionally complete. The propagation delay of a decoder or encoder is the time taken for a change at any input to appear at any output. Because each decoder output is the AND or NAND of n literals, its delay is roughly n gate levels 1 level for each NOT plus 1 level for the final AND. Fan-out is the number of gates that a single output drives. A decoder output often drives many downstream circuits, so its fan-out rating must be checked. Excessive fan-out increases the effective delay. Timing analysis uses the worst-case path. For a 3 to 8 decoder built with 2 input NANDs, the path is NOT if needed to NAND and to optional NOT, giving about 2 to 3 gate delays. Encoders usually have fewer levels, often just one or NOR layer, so they are faster. But a priority encoder adds extra gating for the priority logic, adding another level. Designers may insert buffers to reduce fan-out loading and improve speed at the cost of extra gates and power. A decoder is electrically the same as a demultiplexer, DEMUX. Both take one input line, often a data line, and route it to one of many output lines selected by the address inputs. The only difference is naming. A DEMUX explicitly includes the data line, while a pure decoder only produces a one-hot select signal. Similarly, an encoder is equivalent to a multiplexer, MUX. A MUX takes many data inputs and selects one to pass to a single output according to select lines. An encoder merely reports which input line is active. This equivalence helps when you need to repurpose blocks. A 4-to-1 MUX can be built from a 2 to 4 decoder plus an OR array that combines the selected data lines and vice versa. Example 1, Boolean simplification. Design a 3 to 8 decoder using only NAND gates. Write the minterm for Y5 binary 101 as Y5 equals not a 2, a 1, not a 0. Convert to NAND. First NAND the 3 literals to get n equals not a 2, a 1, not a 0. Then NAND n with itself to obtain the true output, Y5 equals not n equals n NAND n. Count gates, 3 not implemented as NAND with tied inputs, plus 1 3-input NAND plus 1 inverter NAND equals 5 NAND gates. Example 2, circuit size calculation. How many 2-input and or NOT gates are needed for a 4 to 2 binary encoder with enable? The equations are B1 equals Ni2 plus I3, B0 equals Ni1 plus I3, V equals Ni0 plus I1 plus I2 plus I3. Each OR of 2 inputs uses 1 OR gate. The 3-input OR for V uses 2 OR gates cascade. Each AND with N uses 1 AND gate per output, total 3 ANDs. N itself is just a line, no gate. So total gates equals 1 OR for B1 plus 1 OR for B0 plus 2 OR cascade for V plus 3, ANDs equals 7 gates. Example 3, timing. If a 2 to 4 decoder built with 2 input NANDs has a NAND delay of 2 nanoseconds and a NOT delay of 2 nanoseconds, the worst-case path NOT to NAND is 4 nanoseconds. Adding a load that forces a fan out of 4 adds an extra 1 nanosecond buffer delay, giving a total of 5 nanoseconds. These calculations let a designer decide whether to use a faster, more expensive technology.